So in today's lecture, we're going to be using the lecture 16 Vec directory. So you're going to want to pull today's lecture materials and then cd into lec 16 Vec. And we can see this is another C project. And the focus of this one is to first look at what's going on in the include directory, because here is where we're specifying some abstractions we're using. So in guards, we've got just a very simple guard function that's being defined. We can use this when we alloc, realloc, so on and so forth. We've seen this before. So this is just for detecting whether or not a pointer is null and then crashing the program with an error message if so. Right? The real meat of today is in the Vec file. So if you will open up in Vim vec.h from the include directory, go ahead and pause the video here and fill out a few of the questions on gradescope related to this file. All right, now that you've had a chance to read through this file, I want to talk through the makeup of this struct really quickly. You've seen the operations over which we can interact with this abstraction, this vector, which is going to be a growable dynamic array that can hold any type of item. But how does that vector actually represented in memory? Well, we're going to use an idea called a thick pointer. And what a thick pointer is it's effectively a wrapper around a pointer. So notice we've got this pointer to a buffer, and that buffer is going to be where the items of our vector are stored. But the additional members of this struct are going to provide some context that we can use to more safely and meaningfully interact with this buffer without having to keep track of those details separate from it. So let's talk through these details. The first is when we set up a Vec struct, we're going to establish what is the size of an item in terms of how many bytes does an individual item hold in any individual element in this buffer. So for example, if we add a buffer of character values, each item size would be 1 byte. But if we were using double floating point values where each double is 8 bytes, this item size would be 8, right? And we'll need that in order for the implementation of our operations to know where to find the data stored at given indices. The length of our Vec is going to be the number of items we have stored in it. So a brand new empty vector is going to have a length of 0. But as we write items to our Vec, the length will grow as items are added to it. And this is separate from the capacity. And with capacity, what we're keeping track of is how much memory, how many items can we store in our buffer, right? So if we established a Vec that could hold 10 characters, it would initially have a length of 0 and a capacity of 10. And what that 10 would correspond to is the length of the buffer. Now, if we had a Vec of doubles that was initially 10, we would have initially a length of 0 and a capacity of 10, but our buffer's actual size would be 80 bytes, right? It would be 8 bytes multiplied by a capacity of 10. So capacity is the maximum length we can store given the size of the buffer we currently have available. Now, as we mentioned, this is the point of a Vec is to be dynamically growable. So if we add an element beyond our 10th value, so if we added an 11th value, the Vec abstraction is going to handle the implementation details or the accidental complexity of how do we grow our buffer to add more capacity to it. Now, you all already worked through some of these types of details before in th sort, and what we're going to be doing in Vec is trying to encapsulate and put a barrier of abstraction above the idea of a growable vector or a growable array of values so that the details and the accidental complexity of how do we interact with our memory system are hidden from us as the user of the Vec. All right. One other implication of a thick pointer is that notice we have one value, which is going to be stored on the heap always, but often we'll be working with Vec values that are stored on the stack. So we don't even have actually a constructor defined that will give us back a dynamically allocated vec value. We're going to tend to be using stack memory for our vec struct, but the vec itself is going to allocate some heap memory for its one member that's going to be growing dynamically, right? So when we initialize a value using vec value, that's going to malloc some memory or calloc some memory on the heap for our buffer, but it's going to give us back a vec value that would then, the struct itself would be stored on the stack, right? So we won't ever free a vec, or we won't typically free a vec unless we did a little bit of extra work to move a vec to the heap ourselves. But we will need to drop a vec. So drop is a word we're borrowing from other languages that make use of this concept. And before we expire or before a vec falls out of scope, it's going to be on us as the people who are using a vec value to call vec drop, and it's going to be responsible for freeing the memory of its buffer on the heap and resetting some of its values back down. You also noticed in this file some accessor functions that seem very simple, right? It looks like we're putting just a simple wrapper around a property or a member we could have otherwise accessed directly. Like vec length is going to give us back the length of a vec, which is a member of our vector struct. And then same with items is giving us back a pointer to its memory. Well, as we move towards trying to operate in a world where we are adhering to barriers of abstraction, what we're going to try and do is only access the whatever abstraction it is we're working with through its operations and through its functions that it's surfacing, rather than directly accessing its members, which frees up the implementation to change those things if it needs to, right? So these are the two members that we're giving access to, and you can think of these as analogous to getters of two properties that are public, but we don't want someone to be able to set the length of a vec directly, because that length has meaning that's corresponding to the number of items, and so length would be set indirectly. And so we can think of accessor functions as getters and potentially setters if we want to give the end user the ability to change some member or properties of our abstraction. But these are effectively just getters, and we'll use these from the outside to access those properties rather than accessing them directly. And then you saw there are some operations. And so for now, we've just got three really straightforward operations that we can perform on a vec. We can get a reference back to a specific element in memory that would be on the heap and get its address back. We can actually copy a value out of our vec to some other piece of memory, and we can copy a value into our vec from some other piece of memory. So these are the fundamental operations we can perform on a vec, and now we're going to go take a look at the implementation next.